Um, Good morning, everyone. My name is Sharon, and these are my group mates, Arwin, Megan, Thompson, and Wilson. And now we would like to present about periodicity.
Atomic radii is measured by half the distance of the nuclei of two identical atoms that are bonded together. It's often used for us to understand why some molecules can fit together, but some are too packed under certain conditions. And why don't we use atoms' orbits to measure the atomic radii? Also, their sizes are measured by orbital edges. Orbital edges are variable in under certain conditions, so we use the method before to standardize its measurement. Measures of radii include covalent radii, which is the most used as it can be obtained for most elements, so it can be used for comparisons across periods. There are also the van der Waals radii, which is half the minimum distance between two unbound atoms, and the metallic radii, which is half of the total distance between the nuclei of two adjacent atoms in a metallic cluster.
Why does argon do not have a covalent radii? It is because argon is a noble gas. Noble gases do not form bonds with each other as they have full outer electron shells. This explains why argon does not have a covalent radii. Atomic radii of noble gases can be determined from their van der Waals radius. The distance between two nuclei divided by 2 gives the van der Waals radius. What is the trend of atomic radius across the period? That would be the atomic radius which decreases across the period. Why is that so?
So this is the explanation why atomic radius decreases across the period. So across the period, the number of protons in a nucleus increases, so the nuclear charge will also increase. But then the shielding effect is negligible because when each electron is added to the atom, it belongs to the same principal quantum shell. So the force of attraction between the nucleus and electrons increases, hence the atomic radius decreases across the period. And on the right side is the graph of atomic radius against atomic number for period 3.
So this is the ionic radius, how it varies. So as you can see, there's a general decrease, but there's an increase from 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 sulfur to phosphorus because when it changes to ions, um, the positive from silicon to phosphorus, I mean the positive ions lose the shell because they donate the electrons, and there's a general decrease in the radius as the proton numbers increase, so there's a stronger attraction between the nucleus and the outer electrons.
I'm going to explain why the graph of melting point against atomic number for period 3 looks like that. So from sodium to aluminium, there's an increase in melting point. We all know that sodium, magnesium, and aluminium, they all contain metallic bonds, and their bonding can be described as positive ions arranged in a giant lattice held together by a sea of electrons. So they donate particular metal donates electron into sea of electrons. For example, sodium donates an electron to become a sodium ion with positive one charge, where aluminium becomes aluminium with a positive 3 charge. So this causes aluminium to have a stronger electrostatic force, which causes its melting point to be higher than sodium and magnesium. For silicon, it has the highest melting point due to its giant molecular structure. The silicon atoms are held together by strong covalent bonds, which causes its melting point to be high. For sulfur, phosphorus, and chlorine, they all exist as small molecules. Within the molecules, there are only weak van der Waals forces of attraction, which causes its melting point to be low.
Thank you for listening.
Okay, thank you for group 1. Okay, good presentation. So let's actually continue with group 2.
Sir, my share screen might be a bit laggy because it's yeah.
Maybe someone else in the group can share. Okay.
Good morning, everyone. We're gonna present about a about periodicity. I am Ryan, and my group mates are Rick, Michael, and Nathan. What we understand atomic radii? Atomic radius is generally stated as the total distance from an atom's nucleus to the outermost electron. Question two: the atomic of atomic there van der Waals radii, which is about the distance between two nuclei of two neighboring atoms, and covalent radii, measures the size of an atom that forms one bond. Why does iron do not have covalent radii? Covalent radii is defined for whose electron forms a covalent bond like noble gases. Like argon, it doesn't form any bonds. For them, van der Waals radius is considered.
What is the trend of atomic radius against atomic number for period 3? In period 3, the change of atoms from metals to non-metals and decrease in atomic radius. It also increases in first ionization energy and increases in electronegativity. The explanation for question 4 is the atomic radius of atoms generally decreases from left to right across a period. Within a period, protons are added to the nucleus as electrons are being added to the same principal energy level. These electrons are gradually pulled closer to the nucleus because of its increased positive charge. The graph for atomic radii is there are more electrons. The explanation for the graph is because there are more electrons. However, the increase in shielding is negligible because each extra electron enters the same shell. Therefore, the force of attraction between the nucleus and the electrons increase while the atomic radius decrease. That is why the graph is going down.
And this is the graph for number 7, the ionic radius against the atomic number for ions in period 3. And the explanation for this trend is because the atomic and ionic radii of group 13 elements increase from top to bottom in the group. This is due to the increase in the number of energy shells in each succeeding element. However, the atomic radius of gallium is less than that of aluminium, and that is the graph for the melting point against the atomic number for period 3. Starting
Before I
from
discuss question 9 and 10, sorry for the wrong graph in the ionic radius one. I used the wrong picture. It shows ionic energy, not ionic radius. For question 9, this is the melting point against atomic number for period 3. You can see that Na starts to rise at magnesium and aluminum, and then when they reach silicon, the one that has the highest melting point, it goes down to phosphorus, because phosphorus is P4, and you can see in sulfur, which is S8, it has a higher melting point than phosphorus because sulfur has a stronger total bonds, and it starts to decrease from Cl to argon. The higher melting point of metals across period 3 occurs due to the high nuclear charge of metal ions, more delocalized electrons per metal ion, smaller atomic radius, thus stronger force of attraction between metal ion and sea of delocalized electrons. It also has stronger metallic bonds, and more energy is needed to break down stronger metallic bondings. Hence, they have a higher melting point. Going back to what I discussed from silicon, phosphorus, and sulfur, the melting point of S8P4Cl2Ar is shown in this because there is a decreasing strength of van der Waals intermolecular forces of attraction, as there is a decreasing size of molecule. This explanation is based on the known correlation between molecular size or molecular mass and magnitude of van der Waals forces of attraction between molecules. Silicon has a significantly higher melting point because silicon is a giant covalent macromolecule, and in order to melt silicon, there is a need to break down many strong covalent bonds between Si atoms. That can only be achieved by applying considerable energy. That is all, and thank you for listening.
Okay, thank you guys from group 2. Okay, let's actually move on to group 3.
Good morning, Mr. Gopi, and good morning, classmates. My group 3, which consists of me, Audrey, Catherine, and Jasmine, will be presenting about periodicity. So, what do we understand about atomic radii? Atomic radii of a chemical element is a measure of the size of its atom, usually the mean or typical distance from the center of the nucleus to the boundary of the surrounding shells of electrons. We can compare the size of the atoms of different atoms using atomic radii. As you can see from the diagram, the distance between the two nuclei of the same type of atom can be determined and then divided by 2 to arrive at the atomic radius. So what are other measures of atomic radii? The first other measure is metallic radii. This is the radii of the metallic atom. However, the actual measurement of the radius is very vague because the electron don't stay at the point, they orbit around. And the second one is van der Waals radii, which will be discussed further later, is half the average distance between two adjacent non-bonded atoms. And the third one and the last one, covalent radii, which can be obtained for most elements, so this provides the best data for comparison purposes across a period. Why do not have covalent radii? Argon do not have covalent radii as they do not form bonds with each other. However, their group 18, such as argon, atomic radii can be determined by their van der Waals radius. This is found from the distance between the nuclei of two neighboring atoms touching atoms which are not chemically bonded together. This distance is divided by 2 to give the van der Waals radius. This figure will be higher than the single covalent radius of given element, as there are no overlap of electron clouds involved in the van der Waals radius.
The following shows the graph of the atomic radii across period 3, which is from sodium to argon. The trend in the atomic radius across periods shows a general decrease because as the atoms increase in a period, the number of electrons increases, which increases the nuclear charge. However, since they're in the same period, the shielding effect generally remains the same. So the effective nuclear charge will increase and the atomic radius will decrease across the period.
Going across the period from sodium ion to silicon ion, the ions get smaller as the increasing nuclear charge attracts the outermost electrons in the second principal quantum shell, closer to the nucleus with increasing atomic number. There's a sharp increase from silicon to phosphorus ion, as ions get bigger as negatively charged ions are larger than their original atoms. This is because each atom will have gained one or more extra electrons into their third principal quantum shell, increasing the repulsion between its electrons, whereas the nuclear charge remains constant. From phosphorus to chlorine, there's a general decrease as the nuclear charge increases across the period.
How melting point changes across period 3. Melting point is defined as a point where a substance melts and some of the attractive forces between particles are broken or loosened. From the graph, we can see that from sodium to aluminum, melting point increases because metallic bonding gets stronger as the delocalized electrons increase. The difference in melting point between magnesium to aluminum is smaller than from sodium to magnesium because the difference in metallic bonding of magnesium and aluminum is smaller compared to that of sodium to magnesium. Silicon atoms have giant molecular structure, so they are also attracted to each other by covalent bonds, which is harder to break compared to the rest. Thus, it increases drastically. For phosphorus, sulfur, chlorine, and argon, they are nonmetals, so they only have van der Waals forces, which are very weak. It is easier to overcome compared to the other metals and metalloids. The melting point is low because phosphorus. The melting point is low because it because of the van der Waals forces. Phosphorus exists in P4 molecules, sulfur exists in S8 molecules, chlorine exists in Cl2 molecules, and argon exists individually. Thus, P4 has a lower melting point compared to S8. While the rest have a lower melting point, argon has the weakest van der Waals forces, while sulfur has the strongest van der Waals forces. Thank you.
Guys, for this group, can I actually ask, okay, I think this one applies to everyone also. Why S8 has this higher melting point compared to Cl2? Why they are not actually just going down? Jasmine, maybe you can explain.
Because there are like more van der Waals forces and like it's stronger compared to when it exists as individual atoms.
So to answer that, I think you need to mention about sulfur. Okay, they tend to form a molecule with 8 atoms. Okay, where phosphorus they only have 4 atoms, P4. Okay, Cl has 2 atoms, Cl2. So because of the 8 atoms, okay, the van der Waals forces for sulfur will be slightly bigger. Okay, so that will actually explain that. So maybe later I will ask another question related to, we'll discuss it later. Maybe let's see whether the other groups have already prepared something about it. It is actually related to this melting point, okay, of metals. You will find that magnesium, even in this particular group also, it is mentioned, magnesium and aluminium, the melting point is almost the same. Okay, because we do expect the aluminium supposed to have higher melting point, more metallic bonding, but why it is almost the same? Yeah, why there is a it's almost the same. So we will discuss about it later. Yeah. So the next group.
Good morning, everyone. My name is Ben, and I am joined by my groupmates Josh, Chris, Ewan, and Michelle. Today, we will talk about periodicity. What is meant by periodicity? Periodicity refers to the trends of our recurring variations in element properties with increasing atomic number. Periodicity is caused by regular and predictable variations in element atomic structure.
So for number one, what do we understand about atomic radii? Atomic radii is half the distance between nuclei of two covalently bonded atoms of the same element. Or in other words, atomic radius of a chemical element is a measure of the size of its atoms, usually the mean or typical distance from the center of the nucleus to the boundary of the surrounding shells of electrons. Number two, what are other measures of atomic radii? There is the van der Waals radii, which is half the distance between two nuclei of two neighboring touching atoms that are not covalently bonded.
And number three, as of why argon does not have a covalent radii, this is because we know that argon is a noble gas and it does not form any covalent bond. And number four, the atomic radii will decrease across a period because the nuclear charge increases every time.
Now, why is it that this trend happens? Well, the atomic radii decreases across the period as when atomic number increase. More charge will be present and the force of attraction will be larger, thus explaining the trend. Number 6, you can see the graph of basically the trend is graphed out, and you can see that the atomic radius is getting smaller and smaller as the atomic number increases down the period.
As for number 7, you can see in the graph that from sodium to silicon, the radius of the ion slowly decreases, and then it jumps up for phosphorus, and it goes down sharply for silicon and chlorine. And since argon is a noble gas, there is no ionic radius for it. And why is this so? This is because from period 1 to period 3, they are metals, so they give away electrons, and so their radius is smaller. And in this case, silicon also does that. But while they may have the same amount of electrons, the nuclear charge increases, so their radius still goes down. And for phosphorus onwards, they are negative ions, so they gain electrons and they have one more electron shell compared to the metals, and that's why their radius is bigger. And they have the same amount of electrons, so again they have the same amount of electrons, and the nuclear charge increases, so the radius gets smaller.
Here's the graph of melting and boiling points against atomic number for period 3. The trend here, for groups 1 to 3, they are metals, so their metallic bonds are strong, and the melting points are high. As the number of electrons increase, the force of attraction increases as well. For group 4, silicon has a very high melting point because of its giant covalent structure. As you can see in the curve, it takes a sharp dive because for the elements that are to the right of silicon, they are nonmetals, so they have a low melting point. Thanks for listening.
Okay, thank you, group 4. Okay, let's actually go on to the last group, group 5.
Good morning, Mr. Gopi and classmates. Today, my group, Nicholas, Geoffrey, Owen, Juliano, and Kevin is going to explain about the topic periodicity. What is periodicity? Periodicity refers to the trends or recurring variations in elemental properties with increasing atomic number. What is atomic radii? The atomic radius of an element is a measure of the size of its atoms, usually the mean or typical distance from the center of the nucleus to the boundary of the surrounding shells. The other measures of atomic radii are metallic radii, van der Waals radii, and covalent radii. Metallic radii is the nominal radius of atoms of an element when joined to the other atoms by metallic bonds. Van der Waals radii is half the minimum distance between the nuclei and of two atoms of the element that are not bound to the same molecule. Covalent radii is the nominal radius of the atoms of an element when covalently bonded to other atoms, as deduced from the separation between the atomic nuclei in the molecules. In principle, the distance between two atoms that are bound to each other in a molecule should have equal sum of their covalent radii.
Why does argon do not have covalent radii? Argon is a noble gas. The full valence electron shell makes it extremely stable and unlikely to form chemical bonds with other atoms. Because the argon will not form bond, we cannot find the atomic radii by just measuring the distance between two nuclei. But we can measure it by van der Waals radii. The trend of atomic radius across the period. The atomic radius decreases across the period. The reason will be because across the period, the number of protons and electrons increase, and more electrons occupy the same principal quantum shell, but the shielding effect still remains constant. Greater positive charge and stronger forces of attraction pulls valence shell close to nucleus, so atomic radius decreases across the period.
This is the graph for the atomic radius against the atomic number for period 3. As shown in the graph, the atomic radius decreases across the period because the elements in the same period have the same number of shells. So the electrons are in the same principal quantum number shell. But because the nuclear charge increases, the electrons experience greater attraction from the nucleus, so the outer shell is getting closer to the nucleus.
This graph is similar to the one that was presented by Kevin, as the number of protons and electrons increases by 1 with each successive element. However, in this graph, you can see that there is a big jump from the silicon to phosphorus ion. This means that the shielding effect remains constant, so the greater attractive force exerted by the increasing positive nuclear charge on the outer shell electrons pulls them closer to the nucleus. Hence, the atomic radius increases across the period.
This is the graph of the melting point against atomic number for period 3. From sodium until aluminium, the number of electrons each metal donates into the sea of delocalized electrons. And the increasing charge on the metal ions in the giant metallic lattice makes it so that across the period, it will have more delocalized electrons, which makes the metal have stronger metallic bonds and hence stronger melting points. For silicon, silicon has the highest melting point because of its giant structure, also called a giant covalent structure. Every silicon atom is held to each neighboring silicon atoms by strong covalent bonds. From phosphorus until argon, these elements are all non-metallic. They exist as relatively small molecules. Although the covalent bonds within each molecule are strong, they have relatively weak van der Waals forces between their molecules. Hence, they have weak intermolecular forces, which makes them have low melting points. Argon exists as single atoms with very weak van der Waals forces between these atoms. Thank you for listening.
Thank you, guys. Group 5, can you show me the slide number 7? Just share again. Now, while waiting for that slide to be shared, okay. Now, have a look at the graph over there. Okay, this is what I was mentioning just now. Okay, if you look at the graph, okay, there is if you look at the melting point for magnesium and aluminium, you see we expect the sodium, magnesium, aluminium, they are all metals. The metallic bond supposed to be increasing because you are giving more number of electrons. Okay, like for example Na plus 1 electron, Mg2 plus 2 electron, Al3 plus 3 electrons. So we are expecting that aluminium is going to have each aluminium atom has 3 electrons in the sea of delocalized electron. Therefore, the metallic bonding should be greater compared to magnesium. You can see there is an increase from sodium to magnesium. But from magnesium to aluminium, there is no increase. There is an increase actually, but it's not that significant, okay, according to this graph. Can someone help me to tell me what might be the reason? Anyone wants to try? Or let me actually call, you just try, okay? It's not, doesn't matter whether it's correct or not, okay? Maybe Megan, do you want to try?
Not sure, sir.
Okay, so let's ask Jasmine, do you want to try?
Because I think because of the covalent bond, so it's stronger than the metallic bond.
They do not have any covalent bond, Jasmine. Okay, because we are talking about sodium, right? So sodium with other sodium. So it's actually metallic bonding. So we are talking about sodium ions with the electron C of delocalized electron. So there is no nothing to do with the covalent bonding over there. Okay, so this one, okay, it's out of the syllabus, okay, but it is very important to take note, okay, why there is no significant increase from magnesium to aluminum. Generally the trend is going to go up, okay. Aluminum is supposed to be way higher, okay, but for magnesium and aluminum is a special case. They are outside of your syllabus, which is each sodium, magnesium, and aluminium, they have different arrangement in space. Like for example, sodium ion, okay, how they are going to arrange themselves with other sodium ions. They are going to be arranged, maybe in a simple terms, I'll just say they are going to be arranged in a cubic structure, like sodium. Sodium is in cubic structure. But magnesium is slightly different. The structure is going to be in a hexagonal structure. So the lattice, okay, what is lattice is a regular arrangement, yeah. So the lattice is different. So when the lattice is different, it means that the way how the cation and the sea of delocalized electron are positioned are different. So therefore, okay, we cannot assume magnesium and aluminium are having similar arrangement, and saying that aluminium supposed to have greater melting point because of that, because aluminium have different arrangement, magnesium have different arrangement, sodium have different arrangement. What kind of arrangement? The lattice arrangement. Okay, it is actually different. Okay, it is not in your syllabus, but later I will pass you a link, yeah, from a website. If you want to actually read more about that, you can read more about that. How, like for example, each sodium, they are surrounded by total of 8 sodium atoms. Okay, they are surrounded by total of 8 sodium atoms. Magnesium, they are surrounded by 12. Okay, so it's going to be slightly different. So if let's say you're surrounded by different number of atoms, of course, the way how the electrons are going to be arranged, the C of delocalized electron are going to be arranged, and how the interaction of C of delocalized electron and the cation, the metal cations, are going to be different. Therefore, the strength of the metallic bond is going to be different. So it just happened to be taking into that consideration. It just happened to be the magnesium and aluminium, they have similar melting point or similar metallic bonding, taking into consideration of all that. It's a different arrangement. Okay. But okay, as I have explained earlier, okay, I think it is important to also note silicon. Okay, it has the highest melting point because it has a giant molecular structure. But as you go to this phosphorus, sulfur, chlorine, and argon, they have simple molecular structure. But it is also important to note that sulfur is having a slightly higher, okay, compared to phosphorus, okay, because of the reason that I mentioned earlier to you, which is even though I mentioned they have simple molecular structure, P exists in form of, phosphorus exists in form of P4. Sulfur exists in form of S8. Chlorine exists in form of Cl2. Argon exists as Ar. It's a noble gas. So if you look at the structure, the S8 has 8 atoms joined together. Therefore, okay, it is going to have slightly more van der Waals forces compared to P4. Okay, that is going to be the difference over there in when it comes to trend. Okay, so this is what I want to highlight. Okay, but just let me double check with you guys. These are physical trends, okay, of periodicity. Especially by now you should know we are talking about period 3. The trend are the same, okay, for period 4, period 5. Okay, so you need to apply the same trend. But okay, can I ask you how many trends have you covered over here? It means how many physical property have you covered in your presentation? Given how many properties have you covered in this presentation?
3.
3. Okay, very good. Okay, there are 3. So can you name the 3? Maybe Ryan, can you name the 3? One is going to be the trend in atomic radius. So what else?
Ionization energy.
No, this one we haven't covered yet, right? So the one that there are 3 that you covered in your presentation. So they are atomic radius, they are ionic radius. Okay, the third one is going to be the melting point, the one that we are looking now. Okay. And then there is another part together with the melting point. When you do your reading, they have mentioned about electrical conductivity. Do remember electrical conductivity will increase from sodium to aluminium. After that, the electrical conductivity will go down because they are going to change from metal to become non-metal. Yeah. So that is going to be electrical conductivity. Total 3. Okay. I didn't ask you to draw the graph for electrical conductivity because they didn't give you the graph. I don't want you to get confused. But anyway, there are 3. Okay, atomic radius, ionic radius, melting point, and electrical conductivity. But in physical trend, okay, when we talk about periodicity, there are total 4 things that we need to study. Okay, so I'm going to share you another one, the one that I didn't actually ask you to do, which is going to be what Ryan mentioned, which is going to be the ionization energy. So let me actually share my screen over here. So here, okay, when it comes to ionization energy,